Okay. Does that make sense to you guys? Can you see that? Or you got to respond because yeah,
Yes.
yeah, because I can't see you nodding, right?
Yeah, I understand.
What about everyone else? Julio,
Yeah,
Real,
yeah, yeah.
okay. Paula, okay. Now, I'll say this again. If you don't understand, don't be embarrassed or anything like that. If you need me to add on a little bit more or maybe go over something a little bit more, don't be embarrassed. Ask me because otherwise, I'll finish the whole book in a day. Okay. How are you doing so far? You ready? You guys ready to move on to this chapter? Okay.
Yeah, sure. Let's move on.
Okay. So this is going to be chapter 6 and 12. Okay. So we've already talked about chemical formulas and what they actually mean, right? So we know that when we say H2O, we have two hydrogens and one oxygen, right? And so when we talk about water, water is always going to be called water, right? That's going to be its name always. So we never call it dihydrogen monoxide. We call it water. Okay. Um, and then we know that this is sodium chloride, which is salt, right? We call this sodium chloride as chemists. We don't call it salt. We use salt as a very general term for all ionic compounds. We call them salts. Okay. But the key is that we want to remember that the subscript, it tells us how many that there are. Okay, for those formulas. So we've talked about the diatomic molecules. How many diatomic molecules are there? And can you tell me which ones there are? Or we'll say diatomic elements. Diatomic elements.
Isn't that the have no fear of ice cold beer?
That is correct.
All right, cool.
Okay. So now tell me, what does it mean? Have no fear.
So
Tell me
it's
about
hydrogen, nitrogen, fluorine, oxygen, iodine. Is it chlor? Hold on, this is chlorine or chlorine, and then bromine.
it. Good job. Oxygen, and you said chloride, and chlorine, bromine. Yeah. Have no fear of ice, iodine, cold beer. Yep. Okay. And that basically means that there are going to be two of them, right? These guys, helium and lithium, these are called monoatomic. Because we know mono means one, so it's one atom element. We have seven diatomic elements. And so these are the seven diatomic elements. We said hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Now, they're stable as a diatomic element, so they don't like to be single. Um, so they, when they're by themselves, they have to be in twos. Okay. Clear. Okay, write the chemical formula for chlorine, argon, bromine, and krypton. Chanel, you want to help me out with the first one? Chlorine.
Is it CO2?
That's right. Cl2. Okay. Chanel's going to help me out with this one, right? The next one, argon.
Would it be AR? Would it be AR2?
There's only 7 diatomics. What are they?
Is it the ice cold beer?
Yes, I have no fear of ice cold beer. That's right. So it's going to just be AR because it's monoatomic.
Oh, okay, I see.
That's right. Okay. What about bromine?
BR2?
Br2. And krypton.
Would it just be KR?
Okay. And that's it. Okay. Okay. So on our periodic table, you guys are familiar with the metals and our nonmetals and our metalloids, right? So, and you'll notice that on your periodic table, you'll have a line that's distinguishing your metalloids. And then you have your nonmetals. So metalloids are like between metals and nonmetals. So they act sometimes like a metal, and then they act sometimes like a nonmetal. Okay. Now, when we talk about bonding, right? There's 2 types of bonding. Well, there's more than 2 types, and we'll talk about all of the different types. But one of the types of bonding is covalent bonding. Covalent. So that's just going to be sharing between 2 atoms. Okay. So we have 2 more atoms that are going to be sharing pairs of electrons. That's considered a bond. Now, bonds are going to be permanent until you break them by chemical change. So they have to have a chemical change to break those bonds. Okay, so you're going to learn today kind of how to do the nomenclature, but we need to understand that when we have 2, in this case, 2 atoms that are coming together, they're going to form a bond between each other. So these 2 are sharing the electron. So this is the way that we denote that. So covalent bonds are shown by drawing a line between the 2. Now this line represents 2 electrons being shared between those 2 atoms. Those 2 electrons are being shared. In other words, they're orbiting around both the hydrogens, right? So literally what they'll do, this electron will go around here and that'll go around here. And so it's orbiting around both of those hydrogens. So it's being shared between the 2, okay? So covalent bonds, they're bonded together, so they're not going to have any free charge associated with it. So here, this is just basically showing us. So one way to determine whether something has a charge associated with it is by putting it in a solution. So in this case, we have just pure water, 100% water. Now, water is covalently bonded. So since overall there's no charge associated with it, and it's always going to stay together, it's not being broken up, it's not going to have free electrons that are hanging out. So it's not going to have a plus or minus thing associated with it. It's going to be considered neutral charge overall. So you'll notice it doesn't light up when we put the electrodes in and connect it with the battery. That's the same thing if we have a solution that has sucrose in it. Now, as soon as I put salt in there, because salt is an ionic bond, and what happens in an ionic bond, it'll actually separate into its positive and negative charge when we put in water. And since that's the case, you have those pluses and minuses in solution, it's able to conduct electricity. Okay, so it shows us that we're able to conduct electricity. And so this guy is ionically bonded, where these two are covalently bonded. So when we talk about covalent bonds, we're talking about the electrons. They're going to be forming cloud densities around each other. They're going to be overlapping in their orbits. And what do I mean by that? Let me show you. So here, these are them orbiting, the electrons orbiting the nucleus normally by themselves. And so they form this cloud because they're moving all the way, always moving around. They're constantly moving. Same thing here, they're constantly moving. Now, what's going to happen is that in the case of it bonding together, these two hydrogens bonding together, they're going to sit there. These electrons are going to be moving around both of these guys. Okay? And of course, in between them, so they're going to be constantly be moving the whole time through, right? And so they're going to form, like we said, an electron cloud between the two atoms. And so again, this here represents our Lewis dot structure. Now, we've talked about valence electrons. Oh. Now, just a reminder, we talked about it last week, and I was half asleep, and I know that you guys were probably half asleep too. When we talked about those valence electrons, let's go. Pull up P table again. Okay, so here's fluorine, right? Now, the way that we determine our valence electrons is that you're going to be looking at our S and our P. And you're going to count all the electrons that are going to be in that row for S and P. So if we're looking at fluorine, we're just going to go to that second period and we're going to count 1, 2, 3, 4, 5, 6, 7. And that's going to represent the valence electrons. Now, if you look at it, noble gases are going to have 8 valence electrons. Those valence electrons are going to be the outer shell. They're going to be completely full, right? So they can't take any more. They're going to be happy. So that's why they're happy, because they're completely full, right? You know, they ate up, they're good to go. Where fluorine is still a little hungry. It needs one more electron. And so the reason why it reacts is because it's hungry. It needs that one more electron. And so when you're talking about those electrons, there's the way that you get them is either by sharing, taking, or giving. Now, fluorine is one away. Do you think it's going to want to give away an electron? Let me ask you this. Let's say you hadn't eaten in weeks, right? And somebody put a meal in front of you. And then somebody else says, you know, oh, you don't really want that. Let me take that. How would you respond?
Like fight or attack, try to take it back. Try to-
Exactly. You'd be like, no, 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 that's my meal. I'm hungry, right? You hadn't eaten weeks. You'd be starving, right? You're just one away. You want that meal. So fluorine is like, it's one away. It's going to want that electron, right? So it's going to do anything to keep that electron. Now, if it's non-metals or metalloids, it'll share. It'll say, okay, you haven't eaten, I haven't eaten. We can share this meal, right? But if it's metals, it's going to be like, nope, I'm going to take that electron. It's mine. So it's going to take it completely. Here, non-metals share, so they form covalent bonds. Okay? So if you have two non-metals, two or more non-metals, bonding, it's going to be covalent. Okay? and they're going to want to share. The way I like to think of it is that let's say I was a thief, and I want you guys to think about it. Now, if I'm a good thief, am I going to steal from my neighbor? Let's say my neighbor has a Harley, and I think Harleys are really sexy, and I think it'll help me get a lot of attractive women, right? So, am I going to steal from my neighbor? Would that make sense?
No, because
No.
neighbor will see it.
No, exactly, because he's going to see it and he's going to call the popo on me, and then I go to jail, right? Now, not that I'm a thief or anything, but let's say I live in Soledad or Parnell or Salinas, right? But I travel all the way to Fireball, and I see this really nice Harley, right? And so I go to Fireball and I take that Harley, right? And then, but I live in Salinas and I keep it there. Now, what are the probability of them finding that Harley in Salinas? Fireball and Salinas is about 101 miles away from each other. What do you think the probability is?
Low.
Low, right? So my chances of being a pretty good thief in that case would be good. I'd have a nice little Harley and I'd be kind of good to go. I could be driving around town. Nobody would notice it really. Unless I was an idiot and kept the plates on it, right? But that's another story, right? But so in that case, that's kind of like the way we look at it. Non-metals and metals are going to form ionic bonds. So in that case, fluorine is going to take electrons from other metals, or from metals, not other metals. So ionic bonds okay. So, and I kind of like, this is my great divide, you know, non-metals are over here, metals are over here. So they're going to be, the fluorine will take those electrons. So your non-metals will be taken away from the metals. The metals are kind of like, well-to-do and everything like that. These guys are struggling. They don't have extra, right? Where these guys have extra to be like a noble gas. Okay. So are you guys with me so far? Yes, no, maybe.
Yeah.
Yes.
Okay, good. Okay, so we know that covalent is going to be sharing. And we know that ionic is going to be give and take. Okay. One is going to be giving, the other one is going to be taking. Okay. Okay. So these guys, so if we have fluorine and fluorine, they're going to be sharing electrons. So they both have 7 around them. And so what we're going to do is that we're going to arrange it so that they have 8 because they want to obey what we call the octet rule. They want to have it so their outer shell is completely full, like the noble gases. They want to be like the noble gases. So if we sit there and we count the electrons around here, so this is 2, 4, 6, and this line represents 2 electrons. So that would be 8. So there would be 8 around this fluorine. And then there'd also be 8 around this fluorine. That's 2, 4, 6. And then here, since they're sharing it, that's going to be 8. Okay, so in this case, they're obeying the octet rule. Now, these are being shared between bonding. The ones out here, these guys, those are going to be your lone pairs. So that's going to be one lone pair. That's going to be another lone pair. That's going to be another lone pair. So fluorine has 3 lone pairs around it. Lone pairs are electrons that are not involved in bonding. Okay. Again, lone pairs are electrons that are not involved in bonding. So in this case, we only have these electrons that are going to be involved in bonding. Okay. And this just basically tells you what I just showed you. Okay. Now, when we talk about sharing, there are two types of sharing. Okay. So, and I think I shared this with Arnell. Um, so I have two sisters, and growing up, we're a pretty poor family. Both my parents came from really rural class, farm labor. And in both cases, my dad, they would bale hay and chop cotton. My mom would chop cotton and stuff like that. And it was, as growing up as kids and everything like that, that's the way it was. And so their education, they both managed to get a high school education, but that was it. My dad joined the military to kind of escape poverty. My dad's side of the family, my dad had what is it, 11 brothers and sisters. And then my mom had seven brothers and sisters. So they were both really big families, really, really poor. And so my parents, to kind of escape poverty in a sense, my dad went into the military. My mom, she was, she got into a nursing program. My dad was like, you need to come out here and be with me. So she gave up her nursing program and settled for a CNA license to go move with. So money was tight growing up, and there were three of us. And so my parents, they they had this thing that what they would do was they would buy us things that we needed, like underwear, socks, t-shirts and stuff like that, things that you definitely need. And then for Christmas, that's what we get for Christmas. So we get those normally, and we would get one gift that we'd always have to share. And this one time we got an Atari, and I know you guys probably don't know what an Atari is. Do you guys know what an Atari is?
Yes.
Okay.
Game
Well,
Boy
that's good. It makes me feel good that one person knows. Well, for those who don't, an Atari is like
Oh,
a
that's it.
PlayStation, right? So it's like a PlayStation. And so it was the gaming system of the decade. It was bomb when I was a kid. That's what we had. And so my dad actually had gone out on the boat, and my mom was working two jobs to make ends meet while my dad was out on the boat. And actually, my mom was working two jobs anyway, but she got more hours. So literally, she would work till about 3 o'clock, come home and eat and sleep. And my job was to cook, make sure the house was clean, and look after my sisters. And this was during Christmas break and everything like that. So, I'd we got our Atari and everything like that. And my mom says, you guys can play with it, but you gotta share. Right? Big word is share. Okay. So what I did was I made my sisters clean the house in the morning, and while they were cleaning, I was playing a video game. And then it was about 2:30. I'd go in the kitchen and I'd start cooking. And then I throw water on the wall and throw water on myself so I look like I've been cleaning all day and everything like that. And then my mom would come home, and I let my sister play the video game while I was cooking and everything like that. So my mom would come home and she'd see my sisters playing a video game, and so she'd see me in the kitchen and everything. And I just throw water on me, make it look like I sweated and everything like that. Like, well, mom, I cleaned up the house, and then I started cooking. I said, here's everything. I said, it's almost done and everything like that. And she'd always say, maybe just go ahead and sit down and relax a little bit, play the video game, play the video game. And then so I'd go kick my sisters off the video game and play the video game, right? So I played in the morning while they were cleaning the house, and then I played then, but they got the chance to play while I was cooking, right? And then is that fair? Is that sharing? Well, first off, is it sharing?
It is sharing.
It is sharing. Now,
No.
is it even sharing?
No.
No. Okay. So now when we talk about sharing, right, the electrons are just like me, right? So the way the electrons work is sometimes they share evenly and sometimes they share uneven. Okay. Now, the way that you determine if it's going to be even sharing and uneven sharing, I'm going to show you here in a minute. But the way that it's determined is by the strength of the atom, right? Its pull and how strong its pull is for that electron. Okay, we call that electron negativity. The stronger electronegativity you are, the stronger your pull. Okay, the closer you are to being a noble gas, typically the stronger your pull. Okay, so if we have the periodic table here, okay, so these guys are close to being a noble gas, so they're going to typically have a stronger pull. Oxygen is close to being a noble gas, it's going to have a stronger pull. The farther we go out, the weaker the pull. So your periodic table or P table will actually show you your electronegativity. Here, this is the scale of electronegativity. So the highest the scale goes up to is 4. So fluorine is a 3.98 or approximately 4. That's going to have the strongest electronegativity. Then oxygen is 3.44. But you can see here carbon and hydrogen, right? Those guys are 2.0 and 2.50, right? So oxygen has a stronger pull than that. So if they're sharing electrons, oxygen is going to want to pull it. Okay. Now you guys also have, let me see if I can find the table real quick. In your packet, you have this table. This is a nice table rather than having to go to P table and look at it. You have this table here in your packet. So you can see fluorine 4, oxygen 3.4. Okay. Now, the way you determine which one is going to have, if it's going to be a polar bond or a non-polar bond between the two atoms that you're looking at, is that you're going to take the difference. We're going to say the electronegativity we're going to call that En. Okay. So the way that we do it is delta En, which is going to be the difference between the electronegativity between the two atoms. So let's say, for instance, we're looking at oxygen bonded to carbon. Okay. So we're going to take the difference between the oxygen and the carbon. So oxygen is 3.4. And we're going to subtract the lower value, which is going to be carbon, which is 2.6. And if I remember my math correctly, I'm going to say that that is 0.8. So if our electronegativity is less than 0.5, it's going to be nonpolar. Nonpolar is even sharing. If our delta En is greater than or equal to 0.5, but less than or equal to 1.8, it's going to be polar. Or uneven sharing. And then if our delta En is greater than 1.8, that's going to have ionic character, or it's going to act like an ion. Okay. All right. Okay. So in this case, we have 0.8. So where would that fall into? Would that be nonpolar, polar, or ionic character? Polar, that's right. Because it's 0.8, so it's greater than 0.5, but it's less than 1. What about carbon and hydrogen? So we have a carbon and hydrogen bond. What would that be?
None. 0.4, I think.
Yeah.
What is it?
That's right. It'll be 0.4, so it'll be non. Okay, so that's we say that's 2.6 minus 2.2, and that equals 0.4. So that would be nonpolar. Okay, you see how that works?
I have a question.
Yep.
Can we write what you just gave us in our package?
Yes, you can.
Okay.
Good question.
This is chapter what? Is 6 and 12?
This is chapter 6 and 12.
Okay. I don't know if I have a packet for that one.
I haven't printed it out. I'll print those out for you guys, put them in the Mesa, but they're on Canvas and you should be able to download it.
Just print it out. Yeah. Okay.
But you do have this table in your packet if you guys picked up a packet.
Okay. Yeah.
That you guys can use on your exam. Can I erase? Everybody's good? We? No?
See.
See. Okay, good. Okay, so let me go back.
Dr. Henry,
Yep.
I have to go, but I just had one last question. How do
Yes.
you find the difference between uh ionic compounds and covalents?
Yes. So you can do it the same way, but usually you just pay attention. If it's a metal and a non-metal, that's always going to be an ionic. Okay. Because you can have two non-metals give you ionic character. They may not completely dissociate, but they kind of act like they do because it's such an uneven sharing, you know, it's so drastic. And this is going to be recorded and posted, so you're good.
Oh, okay, that makes sense. Thank you.
Okay. And there's also, I'm going to put up my link for my YouTube page. I'll probably do it tomorrow because after this, I'm usually tapped out, but I'll do it tomorrow. And so you guys should be able to see it tomorrow. Okay. So polar is going to be uneven sharing, and then non-polar is going to be even sharing. Okay. And another analogy that I like to use for this is, let's say me and my girlfriend or me and my ex, we get a divorce. You know, my ex-wife get a divorce. That's why we're exes. But we have a kid, and if we share the kid, I get them one day, she gets them the next day, and we go back and forth, right? So then that would be even sharing, right? But if she takes care of him 5 days a week and I take care of him 2 days a week, that would be uneven sharing, right? She would spend more time with him than I would. And he would probably love her more until he gets into his teenage years, and then he'll hate her more than he hates me. So, works out, right? Do you guys see the analogy?
Yes. So wait, polar is equal sharing? No, unequal.
Or unequal, yes.
So it's,
Unequal.
and then polar, wait, I'm confused.
Non-polar,
Non-polar is equal.
that's right.
Okay.
And polar basically means that often, have you heard of the term bipolar? Have you
Yes.
heard? Yeah. What does that mean? Bipolar. Someone is bipolar.
Like they're really like two extremes, like either really good or
Yeah.
like really not good.
Yeah. So I've dated quite a few women that were bipolar. One day they love me and they're like, "Oh, you're the best thing ever," and then the next day they're like, "I can't stand you. If I see your face, I'm gonna cut you." Right? So there are two extremes. So when we talk about polar, it's kind of like that. So you have a bond or a molecule where one is pulling the electron more. So the electron is spending more time around one than the other, so that it acts like it's a negative charge because the electron is over there so often, compared to the other one where it's going to act like a positive charge. Even though it's not ionic, it's going to act that way because the electron spends more time on one side than the other. And I'll show you that. Okay, so here, this is representing nonpolar. So they're evenly shared. The electron is not spending more time around them. You can see the little balls are the same size. So they're sharing it even. In this case, this is a polar bond. This is uneven sharing. So Y is getting the electron more. So that's why Y is so much bigger than X, right? Because this guy is getting the electron more. So in this case, we would represent this as, we call it delta. It'll be delta minus for Y. I am struggling so much today. So this is the Greek lowercase delta, and we'll put a minus here since the electron is spending more time around that one. And then this guy would be delta positive. Now, delta means partial, right? In this case, it's not completely positive. This one is not completely negative. It's partial. They're sharing the electron. The electron is still going between both of them, but it's spending much more time around the Y than it is around the X. Okay. And then if we talk about ionic, the electron is actually being transferred. So in this case, the metal is giving up the electron completely to the non-metal. Okay. So there's no sharing in the case of an ionic bond. It's just based upon electrostatic forces. Okay. We've already talked about the electronegativity, and that's attracting the electron. It's pulling the electron closer to it. So fluorine, as I said earlier, is the highest electronegativity. It's like little Napoleon. It's the smallest atom, one of the smallest atoms. It's not the smallest, but it's one of the smallest atoms. But it has such a strong pull because it has so many electrons in the nucleus, and its size, that size nucleus ratio is huge, right? I mean, so it has such a huge pull. Okay. So we've already talked about electronegativity. And so this is just kind of reinforced that. Let's see. So when we're sharing just a single pair of electrons, that's going to call the single bond. When we're sharing two or more, uh, two pairs of electrons, that's a double bond. And if we're sharing three pairs of electrons, that's a triple bond. So for instance, if we have oxygen and oxygen, it actually forms a double bond. And so we would draw it like this. Where again, the line represents two electrons being shared between the two. So that's a pair of electrons. This is another pair of electrons. It obeys the octet rule, 2, 4, 6, 8 around here, 2, 4, 6, 8 around here. Earlier we saw fluorine bonded to fluorine with its lone pair on the outside. So that would be a single bond. And then we have nitrogen, which forms a triple bond. Okay, with two lone pair. Okay. Now, we do have atoms where you have more than just two atoms bonded together. Here we have water, which is one oxygen, two hydrogens. And so again, you want to obey the octet rule. Hydrogen doesn't obey the octet rule. Hydrogen can only have two electrons around it. It wants to be like helium. In this case, the electrons are going to be shared between oxygen and hydrogen. These are going to be shared between oxygen and hydrogen. So in this case, it has only two around it. And this guy has 8. 2, 4, 6, 8. Sometimes we have atoms that have lone pair. And so when you're trying to figure it out, we want to draw the Lewis structure. And so in this case, we know that nitrogen has 5 valence electrons. So we're going to start off with the 5 valence electrons. So that's 2, 4, 1, 2, 3, 4, and 5. Okay, so those are the lone pairs. Valence electrons. Those are the valence electrons. And then hydrogen has 1 valence electron. Okay, so we're going to have a bond here. We're going to have a bond here. And we're going to have a bond here. Okay, and then you have those two lone pairs up here. So that's 2, 4, 6, 8 around nitrogen. And then each of the hydrogens only have the 2 around them. So it's like helium. Okay, so you're probably going to ask me, how do I know how many valence electrons we have? You guys remember? We mentioned it a few minutes earlier. Is anybody there? Are you guys all back?
Yeah, we're back. Well, I'm back. Were we asking about the valence electron?
Yes. So how do you know how many valence electrons you have?
Is it like on the periodic table? Oh, I can't find mine. But like, would it depend on the S and the P, like that type of thing? Or
Yeah.
would it be like, flow? Yeah, would it be that?
Yes, it's going to depend on the S and the P.
Yeah.
And so we're going to look at that outer shell for that element. We're going to look at the S and the P. So you guys remember this is our S. I'm going to use the cursive S, and this is the P. Okay, so if we're talking about chlorine, right? Chlorine. Then all you would do is count over 1, 2, 3, 4, 5, 6, 7 until you get to chlorine. So it has 7 valence electrons. So that means it can use those 7 electrons for bonding. It doesn't have to. It could use 1, but it could use 7 if it needs to. And then that's the same thing if we come down here. So we're going to just look at the S and the P. So let's say we're talking about polonium. So then in that case, even though polonium is a post-transitional metal, it does some weird things every once in a while. So that'll be 1, 2, 3, 3, 4, 5, 6. So it would have 6 valence electrons, okay, that it can use for bonding. Okay, questions?
I have a question. Like, okay, you see those numbers up on the top, like the 13, 14, 15, 16, 17?
Yeah, the groups. Yep.
Okay, like if you just take off the one, like in that group, they all have 7. Is it like that or no? And like in the
Yeah,
next group, they
exactly.
all have 6. The next
That's
group,
right.
5, 4, 3.
Yep.
Yeah.
Yep.
Okay.
Yeah, so you're saying group 7, right? I mean group 17. So
Yeah, like
this
those would
always has
have
7.
it.
Yep.
Okay.
Everybody down here has 7. Yeah. Then this one, everybody has 6.
Yeah.
Yeah. Yep. Okay. Come on. Okay. So now these are examples where they're obeying the octet rule, meaning that they want to have 8 around. These are examples where they don't obey the octet. So if we have nitrogen and oxygen bonding together, what happens is that oxygen, since oxygen has a stronger electronegativity, oxygen is going to get its 8 around it. So if we count the number around it. Well, first off, let's take a step back. Nitrogen has 5 valence electrons, right? So if we go to our periodic table, we're going to do this on the other side. Okay, periodic table. Nitrogen is right here. So we count over 1, 2, 3, 4, 5. It has 5 valence electrons. So we're going to put N with 5 dots around it. There's 1, 2, 3, 4, 5. Okay. And then oxygen has how many valence electrons? That's right. It has 6. So that's 1, 2, 3, 4, 5, 6. Okay. So 5 plus 6. Since 5 plus 6 is going to equal an odd number, that's going to equal 11. We know that it cannot obey the octet rule. It won't be able to obey the octet rule because there's an odd number of electrons. Okay, so the best that we can do is the one that has the strongest electronegativity is going to have 8 around them. The one that has the weaker electronegativity is going to have less. Okay, but we're going to try to get it as close to 8 as we can. So in this case, we have hydrogen and oxygen and nitrogen double bonding. So we have these 3 electrons coming over here. And then we'll take one of these guys also to kind of pair up. So then we have a double bond forming here. We have one here, one here, one here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if we count what oxygen has around it, that's 2, that's 4, that's 6, that's 8. Nitrogen here has 2, 4, 6, 7. So since nitrogen is going to be weaker in electronegativity, it's not going to be able to pull that electron more. So oxygen is going to make sure it gets its octet, and then nitrogen is going to be out of luck. Okay, it's kind of like Do you guys have younger siblings or older siblings?
Yes.
Yeah. So
Yes,
was your are you the youngest or you guys are older?
I'm the middle.
You're the middle. Okay.
Yeah, I'm the middle.
You're the middle. Okay. So as I said, I'm the oldest, right? So with me and my sisters, right? When we were young, I was bigger than my sisters, and then I would take everything and it would be mine, right? So I made sure I got mine first. And then if I had extra, I let them have it, right? And so that's what's happening here. Oxygen is kind of like the older sibling, and they're like, no, that's mine. I'm gonna make sure I got mine. And then anything extra you can have, you know. So Mark probably is like, he gets screwed a lot since he's the youngest. He's like, his older siblings are like, nope, mine first, and then
I think the baby always gets everything. Sometimes.
well, from their parents, not from their siblings.
Oh, yeah, yeah. True.
Okay, let's see. Okay, let's keep going. Oops, carried away. Okay, so and sometimes, so this would be an example of hypovalence, right? So we have less than what we're able to reach our numbers. So it's going to be under what we can have, right? So in the case of the nitrogen, okay, or we'll call it the odd electron, okay. So this is an example of what we call hypervalence, right? This does not obey the octet rule, and these guys aren't going to obey the octet rule is because our center atoms here, our phosphorus and our sulfur, they're going to be able to take more electrons because they can use the 3D orbital. So anything that's periodic table again. So any element here and below, all of these guys have access to their 3D orbital because the d orbitals start at 3, right? So this is 3D. This one has 4D. Excuse me. 5D down here, and then this is 6D down there. Okay, so these guys, since they're in the third period, they can use the 3D orbitals to store electrons, to start storing electrons. And so both of these guys do that if it makes them more stable. Okay. And the way that they determine that stability is called the formal charge. And I'll show you that here in a minute. Okay. So these guys, it's again, their center atoms are able to hold more. And so they won't obey the octet rule. Not all the time. Most of the time they'll try, but if it's less stable, they won't. This here is called hypovalency. This is an example of a metal that is acting like a non-metal. Beryllium and boron, well, boron is a metalloid, so you can get this bonding, covalent bonding happen with boron, but beryllium is really, it's a metal, but it thinks of itself as a non-metal. So it forms covalent bonds, and particularly between fluorine, but it doesn't obey the octet rule because it only has 2, 4. So it only wants to have 4 electrons around it, where boron wants to have 6, and that's it. So that's 2, 4, 6. That's around boron. Okay. So again, this is hypovalency. Okay. And then back. One before it was hypervalency. Down here was hyper. Okay. So I have a question for you guys. And I know I haven't said anything, but I want to see if you guys can help me out. Excuse me. How do I know which atom goes in the center?
Would it like be the one with the most? Since it's like or least maybe because it's sharing with all the other ones, right?
Okay. So not necessarily. No, no. So the way that we determine which one goes in the center is going to be by electronegativity, right? So you get pushed in the center if you're weaker than the others. And also if you're able to hold more bonds. Like for instance, carbon has 4 valence electrons. And since it has 4 valence electrons, it's able to make 4 bonds. So it kind of likes to be in the middle, right?
So wait, so it's the ones that have the least amount of electronegativity that go in the middle?
Yeah, but again, when we're talking about covalent bonds, it's always going to be non-metals.
Non-metal.
That's right. So we're only talking about non-metals. We're not talking about everyone. We're only talking about non-metals. So carbon likes to be in the middle, right? And one of the reasons why carbon likes to be in the middle is because carbon is a little bit of a whore. Carbon likes to be the center of attention. It can hold 4 bonds. It can have 4 attractions. Okay, carbon is right here. It gives it a little more flexibility than some of the other guys. It needs 1, 2, 3, 4 electrons to be like neon. It also needs 1, 2, 3, 4 electrons to be like helium. It's like right there in the center. It gives it a little more flexibility than everybody else. So it's kind of like a little whorish, right? It's like I can attract people. I like to be the center of attention. I like to, you know, it could have 4, 4 people it's messing around with, so it's it has that flexibility. Okay. And because of that flexibility, it makes it a great molecule for life. So that's an example. Carbon is always going to try to be in the middle. Hydrogen can never, ever be in the middle. Why can't hydrogen be in the middle? Who is hydrogen wanting to be like? Which noble gas?
Helium?
Helium. And helium only has 2 electrons. So if we put hydrogen in the middle between something, then it's going to have more than 2 electrons around it. It can only have 2 electrons around it. So it's always going to be at the end. Fluorine will always be at the end because it's so strong, it doesn't like to share at all, really. And so you're trying to get fluorine to share more than 1 electron is not going to happen, right? It's one and done because it only needs 1 electron to be stable, um, like argon, not argon, neon. Okay. So naming, nomenclature. Okay. When we start with nomenclature, what we're going to do is we're going to start with covalent bonds first. Okay. Now, when we're talking about covalent bonds, we're going to be using the Greek prefixes. Okay. Except for 2 traditionally named compounds, water and ammonia. These guys are just going to be called water and ammonia. That's going to be their name. Okay. And that's their traditional naming. You're not going to use IUPAC nomenclature for it. They're always called water and ammonia. Now, the very first word is going to be the element. And then either we're going to put a prefix to tell us how many that we have. So we're going to use that prefix to tell us how many we have. And then the second word or the end of the compound. And I'm not going to say second word because there are compounds that are more than just binary. Binary just basically means 2 nonmetals together. You could actually have more than 2 nonmetals. But the second word or the last word, the last element, is always going to have "ide" at the end of it. Okay, so let me give you an example, something that you guys know. So if I have this guy, what is this called?
Carbon dioxide.
Carbon dioxide. Okay, so we know that this is called carbon dioxide. Now, if we look at it at the end, the second word has "ide" instead of oxygen, so that ox, we drop everything else and we put "ide," right? Di lets us know that there are two. There are two oxygens. And if you notice carbon only has carbon, right? So if we had more than one carbon, we'd have to put a Greek prefix to say that. So these are your Greek prefixes. Here. So these are the Greek prefixes. Let's see. One is mono, two is di, three is tri, four is tetra, five is penta, six is hexa, seven is hepta, eight is octa, nine is nona, 10 is deca, 11 is undeca, 12 is dodeca, and 13 is trideca. Okay, so those are going to be your Greek prefixes. So if I have something like this, what would I call this guy? This compound.
Is that phosphorus?
That is phosphorus. That's an F.
So then it would be like would it be undeca? Wait. Like undeca phosphorus. The F is fluorine?
That's
Fluorine?
right. That's right.
And then
So,
7 would be hepta.
undeca, phosphorus.
Uh-huh. But wait, the Greek, you only use that for the first element?
No,
The
you use
Greek
the Greek. You use it for both of them.
Oh, for both. Oh,
Yeah.
okay.
So it's undeca, phosphorus, but you don't drop anything on the first one, right? The name. And
Oh,
then you put, it would be hepta
hepta,
fluoride.
fluoride.
Yep.
Okay.
Because you drop the INE and you replace it with IDE.
How do you know when to replace it with like IDE or ATE? Like,
Okay.
or
Well, when we talk about the eights make reference to like the ATE. Those make reference
yeah.
to what we call oxy and ions. They have oxygen in them, right? And I'll show you what those look like here in a second. You know, because we're going to pull up our table. You guys have your polyatomic ion table.
Is it the I ate organic apple despite being in poison?
That's when we start talking about acids.
Oh yeah, that one.
Yeah, but we use those roots to let us know. Okay, but right now we're just talking about covalently bonded compounds. Okay, again, these are covalently bonded compounds.
So
Okay,
the covalently bonded compounds, it's gonna be IDE.
IDE. Yeah, and so the IDE, what it does, it tells us it's the end of the compound, right? And that's its purpose. Because if we have a list of things, you know, this and this and this and this, you won't know which one is the end. So we use the "ide" to let us know that's the end of the compound. So if I have CO, this guy's called carbon what? And so when it's the second word only has one, then we're going to use mono. Or I should say the last one. The last thing has one, the last element has one. We call that monoxide. Okay. Now the other thing is that oxygen doesn't put monoxide, it puts monoxide. So it actually will drop this O. It'll drop this A, it'll drop this A, it'll drop that A, it'll drop any of the A's, and it'll drop O's. It'll keep the I. Okay? So it'll drop A's, but keep the I. Okay? So we call this carbon monoxide. Since there's only one, so we just keep it as carbon monoxide. What about this? What would we call that?
Dinitrogen.
Okay.
Dioxide.
Nope, not dioxide,
Dioxygen.
dioxygen.
Difluoride.
And then there's two of them. So we'd say, you said difluoride?
Yeah, difluoride.
Difluoride. Okay, so that's what we call that. So that I lets us know it's the end of the compound. Okay? Good? Yeah? No, maybe?
Yes.
Okay.
Yes.
Okay, so if we have dinitrogen pentasulfide, so what does that look like? What is the chemical formula for that? Yeah. And don't all you guys yell at me at once.
Hi.
So
Hi.
oh my God. Sorry.
That's right. That's it.
So then for the dinitrogen, would it be like N2
Okay.
and then sulfide is I'm not even sure. I can't find my periodic table right now. But I think it would be is it S?
There's
That's
an
right.
S5?
Five.
That's right. That is correct. Good job. We got our young chemist already.
Yeah.
Yeah.
You're welcome. Okay, what about the next one? So it's dinitrogen pentoxide.
Is it N2 N2O and 5?
N2O5. Okay. Okay, what is the name of this compound?
Tetraiodine.
Nona oxide?
Known oxide. Right. Remember the A gets dropped.
Yes.
Okay. And this last one, we've done something like that already.
phosphorus pentafluoride.
Okay. Questions?
No.
No.
Good.
Wait, so the IDE is always at the end of every single element, or there are some exceptions?
There are going to be exceptions. So now so let me elaborate on this, right? So this is when we're talking about covalently bonded, right? Now they're going to happen with ionic bonded compounds as well too, and you'll see that here in a minute. But those are only when it's monoatomic, and I'll show you what I mean by that one. Okay. So again, if it's covalently bonded, it's going to use the Greek prefixes. Say that one more time. If it's covalently bonded, it's going to use the Greek prefixes. Okay. Now, carbon is going to be special. Carbon is the center of organic chemistry. We call it organic because organic matter, carbon, right? It has its own type of nomenclature, but it's very, very similar to this. And it also uses some of this nomenclature as well. Okay. And I'll show you that a little bit later. Okay. So we talked about ions already, right? So a cation or a positive ion is positive because we've lost two or more electrons. So, and the way I remember cation is because a cat meow, it's positive, right? Cats have paws, positive. Okay, I know it's a bad joke. You could at least, make me feel a little bit good about myself and laugh a little bit. You guys are rough crowd here. So we also have an anion. Anions are negative, right? And they're negative because they've gained more than one or more electrons. So they're negative because they've gained one or more electrons. Okay. Now, what we're talking about here, these guys are going to be, these are examples of mono ions, right? So in the case of nitrogen, nitrogen is 3 away from being a noble gas. So what nitrogen is going to try to do is, in an ionic situation, it's going to try to gain 3 electrons so it can be like neon. It wants to be stable like neon. Okay. So it's going to try to get those 3 electrons. And so once it gets those 3 electrons, its octet is filled up. And this is the way that we would draw it. It's Lewis dot structure, or we just draw it like this. This is what we typically do. That lets us know that nitrogen has 3 extra electrons. So that's the reason why we write the 3 minus, because we know that that minus represents electrons. So oxygen is only 2 away from being a noble gas. So it's going to want to gain 2 electrons. Okay. And so then we write it out like this, O2 minus. Okay. Fluorine is only 1 away. So it's going to want to gain that 1 electron. And so when it forms an ion, it's going to have 10 electrons and 9 protons. So in other words, we're going to have 1 extra electron. So we're going to have F minus. And then neon is going to be the noble gas. It's going to be paired up. So these guys are called, the fact that they're trying to be like neon in terms of the number of electrons that they have, that makes it isoelectric. Iso basically means same, and then electronic means electrons, right? So these guys have the same when they form ions, same number of electrons as neon. So sodium is on the other side of the periodic table. Let me share you the periodic table, and they'll go through it. Easier that way. I need picture in picture this class. So I can have my periodic table in the corner all the time. So if we look, sodium is right here. This is where sodium is located. Now, I'm going to ask you a question. I want you guys to think about it seriously. Okay. So if I am, if I have the option of going to the same store, one way it's 1 block away, and another way it's 7 blocks away. What would you do? Right. And let's say you've been working all day, you had a long day at work and you just wanted to get an ice cold soda or an ice cold beer or an ice cold whatever you like that is really cold and just it makes you relax. Right. Would you walk that 1 block over or would you walk 7 blocks to go get it?
The 1 block.
Okay. The 1 block. Okay. And that's exactly what these elements are going to be. So everything that the elements do in terms of chemistry has to do with trying to lower its energy state and also trying to be like the noble gases, right? By being like the noble gases, you're lowering your energy state, okay? So nitrogen is here. I mean, not nitrogen, sodium is here. And it's only one away from being a noble gas, or it could try to gain 7 electrons and be like argon. So would it be easier for it to lose 1 electron and be like neon? Or would it be easier for it to gain 7 electrons?
To lose one and be like
It's
neon.
easier to lose one. Less energy, right? And everything is going to be about less energy. Atoms are lazy, right? Just like us. If you guys could get away with getting an A just by saying, "Hey, Dr. Henry, you are the greatest instructor in the world," and coming in here, you say that and sit here with me and we talk the crap, you would be here every day. I have the whole class here, wouldn't I? Instead of just, the 7 of you guys, right? It would be the whole class. Okay. Now, that's because it's easy. That would be an easy thing to do, right? But having to come in and put the work in, nobody wants to do that, but dude. Anyway, we do what we got to do. So that's the same thing with these atoms. They want to try to find the easiest way, the laziest way to sit there and do it. It's easier for it to lose one rather than trying to gain more. Okay. And where these guys here, it's one away from argon. So in this case, it could either gain 1 electron or lose 1, 2, 3, 4, 5, 6, 7. 7, right? So you could lose 7 or gain 1, right? It's easier for you to get that 1. So it's going to try to use the least amount of energy. And that's always going to be the case, okay? Any questions? No questions? Good. Okay. So this guy is going to end up being sodium plus because it's going to lose 1 to be like neon. What about magnesium? How many electrons does it need to lose or gain to be like a noble gas?
2. Lose 2.
2. It needs to lose 2. What about aluminum?
3.
3. Okay. What about silicone?
Would it be 4?
It would be 4. So, but it's kind of a special case again, kind of like carbon. It could either gain 4 or it could lose 4, and it would end up the same. So if it gains 4 electrons, it's going to be like argon. If it loses 4, it's going to be like neon. Okay. And that's part of the reason why they always believe that, group 14, those are the center of life because they can go both ways, you know? Okay. Let's go back to the top. And then we're going to probably wrap up a little early. We're going to say probably like 10 minutes early, maybe today. Okay. So, and this is what's showing you. And so these guys are also isoelectronic to neon. And so if we go to our periodic table here, you can kind of see which ones are isoelectronic. So here, this is if hydrogen gains one more electron, it's going to be like helium. If lithium loses one electron, it's also going to be like helium. And so they're color coded to let you know which ones are isoelectronic to each other and to kind of give you an idea of the monoatomic ion that's going to form. Now, group one metals are always going to end up being a plus, right? Group two metals are always going to end up being, what do you guys think? But do we look down here?
Plus positive.
Yeah, but it's going to be 2 plus, right? Because you're losing two
yeah.
electrons to be like a noble gas. These guys, this is going to be a 3 plus, and these guys will also be a 3 plus, right? Even though that they're transition metals. All of the other transition metals, they're going to vary, right? They're going to have changes. Some of them going to have multiple possibilities because the D, the metals that are in the D subshell, those transition metals, so those guys find different ways of finding stability. They're kind of like independent from each other, where everyone else is going to try to obey the octet rule. They're going to try to be like the noble gases by making sure that they have 8 around. Okay? Okay. So when we talk about ionic compound, ionic bond, that's going to be attraction. So how many of you guys dated when you guys were in high school or in college? How many of you guys date? Anybody date?
I did.
Okay, you did. Okay, so I got one person in the whole room that dates. So that's good to know. So there's a lot of single individuals out there. So do you guys know that chemistry is about that connection? It's about chemistry, right? Finding that chemistry, right? Okay, another bad joke. Never mind. Okay, so anyway, when we dated in high school, there's something that we typically did. So if you were a good person, like a good girl and stuff like that, you did your homework and do what you're supposed to do, right? Then then you typically, and I'm gonna say 9 times out of 10, you went for the bad, right? And it would always end up like this. And I'll tell you the scenario. So, you know, you come home to your parents and everything like that, and you're like, Mama, Mama, guess who asked me out? Guess who asked me out? Right? Or guess who I asked out? Guess who I asked out? Right? And you tell them, oh, Johnny, Johnny Jones, he is just so cute. He's so adorable. And your mom said, who? Who, baby? You said, Johnny Jones. You're not talking about the Jones from up the street. The ones that, have robbed 6 people and, stole from the bank and stole from the church. Not that Johnny Jones. Mama, you just don't know him like I know him, right? No, that's Johnny. Johnny from up the street. No, you are not dating Johnny. There's no way that you're gonna date Johnny, right? And what did you do? Did you break up with Johnny? No. Yeah, maybe. Did you dump that one after your parents told you that you shouldn't be dumping them? Or did you stick around your parents' back and still date them?
Snake.
Snake. Now tell me why. Why did you do that?
Opposites attract.
Opposites attract. Exactly. Right. And so because opposites attract, it's going to always be the case. You're always going to find that bad boy. Oh, I can change him. I can make him a better person. Right. And then he's probably thinking the same thing about you. Oh, I can change her. I'm going to make her not a worse person, but yeah, worse person. I'm going to make her fun. And so the thing is that you guys are opposites and you attract. And that's what ionic compounds are about. They're about those opposite forces attracting, those positives and those negatives coming together. And I'll tell you this, just from my personal experience, when you get 2 people that are exactly alike, they're both real positive and everything like that, that drives me crazy. I see those couples, you've seen those couples. Those couples never laugh, right? Because they're too much like each other, right? They're too positive. When one of them's down, when people are down, they want to see somebody else who's down every once in a while, right? It makes them feel better, not because they love misery or anything like that. I guess misery does love company, but it's because sometimes you want to see that other people have problems too. It's not just you, right? But if you have both of them are all happy all the time, they repel each other. They get sick of each other. They end up cheating and stuff like that because they can't quite get along because they repel each other because they're too much alike. They're both positive. And that's the same thing with negative people. You have two negative people that hook up and stay together and stuff like that. It is horrible. I had one of my best friends. He was so negative, right? And the girl that he met was so negative. They were both, when they get together, it was just horrible. They would just see who was the worst, right? And it would just keep going worse and worse. It was horrible. And eventually they get tired of each other and they break up, right? Because you need those opposites, right? And those opposites, they fit in together. And that's exactly what's going to be happening with ionic opposites. Okay, now let me tell you a little bit about ionic compounds. So nearly all ionic compounds are going to be solid at room temperature, at normal room temperature. And that's also at pressure, standard temperature. They like to form crystal lattices, so they're organized in their structure. So when they're bonded together, when their charges are combined, they're going to have an overall neutral charge, right? So when they add up, they're going to add up to zero always. So they're always going to end up adding up to zero because overall it has to balance each other out completely, and it's going to be a neutral charge. We're getting a little tired, so it's kicking in. The last thing is that that we're going to be talking about today, and I'll show you a picture, and then we'll close up for today. So those bonds, they're going to be strong, right? So long as you're talking about the crystal structure, you're not talking about them in solution, they're going to be strong bonds. They're going to be hard to break because of the attraction. So that attraction makes them very strong, okay? And so that's why you always end up with these solids and stuff, and they're not easily broken down. So a lot of our stones and stuff like that, those are examples of ionic compounds. They're pretty strong. And then some of them, when they're in their liquid form, you heat them up so much that they actually melt, and that takes a lot of energy to do that. They're able to conduct electricity. So they're good conductors of electricity when they're heated or when you dissolve them in water. So like if you dissolve salt, sodium chloride in water, it's able to conduct electricity extremely well. Okay, so here's an example. So this is a reaction between sodium and chlorine. So when you bring sodium and chlorine together, what happens is you get this really nice flashing yellow light. It's very bright, and a lot of smoke starts to form and everything like that. And it's a very quick and strong reaction. It's very volatile, right? Or a violent type of reaction occurs because the chlorine gas is reacting with the sodium metal and you're forming sodium chloride. And so what's happening there is that the sodium, which is trying to get rid of electrons, is dumping its electrons to chloride. And chloride is taking it. It's like, yep, give me that. I want that, right? Because chloride is only one away from being a noble gas. So if it gets one more electron, it's going to be just like the noble gases. And then sodium is also one away from being a noble gas too, if it loses that one electron. So they're like the perfect mate. One is losing, the other one is taking, right? And if you think about it, a lot of relationships are like that. It's about that give and take. One gives, the other one takes. One gives, the other one takes. And sometimes it works out pretty well, as long as it takes turns, right? So this is an example of the crystal itself. And so this is what a salt crystal looks like. But what is happening here, this is the model of that salt crystal, is that the chloride are going to be the green balls. The sodium is going to be the gray balls. So they're going to be alternating in their structure. So your positive is going to be surrounded by your negatives. And those positives and negatives are going to play off of each other. So we have positive, positive, negative, positive, negative, positive, negative, positive, negative, right? So they're going to be surrounding each other, making a nice lattice structure. This is just showing you a better picture of it. Exactly the same concept. You have those alternating structures where your positives are always surrounded by your negatives. Your negatives is always surrounded by your positives here in these grades. Okay. This is an example of when those like salt is heated up or dissolved in solution, it's able to conduct electricity well. Okay. And so these are called ions. They're forming ions, and these ionic bonds are coming together so they balance each other out to make a neutral charge. Okay. So we're going to stop here and we'll pick up on monoatomic ions next week. I'll say all my classes are going to have exams next week. So technically, they're going to be due on Friday, but they're going to be open over the whole break. So you won't be penalized if you turn them in late. But make sure that you get it done before that Monday after spring break. Okay.
Wait, so when will the exam be opened?
So I will be opening the exam officially. It will open this Friday. Thursday, tomorrow, I'll be finishing up the practice exam. Practice exam will open up. And so it's going to be open, as I said, till the end of spring break. Okay.
And
So
then,
all of them. Yeah.
so basically, it will be opened on Friday, and then it
And
will
then
be
it'll
open next Friday.
officially, yeah. So officially due. So it's going to open on Friday. It's going to be officially due not this Friday, but next Friday. Oh, officially, but unofficially, it's going to remain open. Okay. So I would like to have you guys do it on Friday. However, before Friday, I should say. I'd like to have you guys do it before, not this Friday, but next Friday, right before spring break. I would like that. However, I'm going to be lenient and give you guys over the break to sit there and do it. But get it done before the break. I won't be lenient after the break. You know? That's right, exactly. Right? So you're going to get it done, right?
Yes. Oh, when are you doing the study exam?
So I'm going to have my tutors, and I'm going to try to bring a couple of more tutors on board um, for this next couple of weeks. And so what we're going to try to do, if you did not do well on your last exam, I'm going to introduce you guys to some tutors to try to help you out. And so I'm going to have them try to meet up with you at the time that they're able to meet up. And so I'll be trying to get that done because I have to finish grading my Kalinga classes here to finish your reading and your grading. And then I have a couple of hard nails that I have to do. So I'll be trying to get those done, and then I'll hit you guys up with those tutors. But I'm also going to see if I can get my tutors to do a couple of extra reviews next week. For me, next week is going to be crazy because I have a site visit. So my mentor for the National Science Foundation is coming in the first 3 days. And then on next Wednesday, I will actually be flying out to Philadelphia for a conference. And so I'm going to have a recording up instead. So I'll let you guys watch that instead. And if you guys have any questions, I will try to make um, and so that's actually going to be my Wednesday, and I have a Thursday class that I do another lecture for as well. So that's both classes are going to get videos, unfortunately, because I'll be at the conference. But I will try to set up a time on that Friday, and it'll probably be later in the afternoon because again, I'll be in Philadelphia at a conference. But instead of partying, I'll be spending it with you guys.